Anyway, we think that the population has been growing faster and faster recently, but for most of human history, for the first 8,000 out of the last 10,000 years, for most of human history, population growth rate has been very close to zero. .1/20% per year. That's close to zero. So, what did we say earlier? We said that the growth rate R, the natural growth rate, the crude rate of natural increase, is the difference between B and D. So that difference must have been very close to 0.0005. So the birth rate and the death rate were close to each other for a long time. The crude rate of natural increase, our growth rate, was close to zero. That means that B and D had to be close together for a long time. Now, B is our birth ratio. I said that it's very close to a birth rate. I'm going to come back to this later, but B is what we often refer to as the crude. I think I referred to this earlier as the crude birth rate. And once again, I'll become, in another lecture, I'll be more careful about exactly why it is close to a rate. And then we said our D, lowercase d, is the crude death rate. In a rate, these are going to be the numbers of events per person. And now I'm going to tell you something which is true. It is in general true. And I'm going to say that if we have something which is a rate, and both of these things are rates, the reciprocal of a rate is the average interval between events. Let me just clarify one more time. These things, these rates, are the number of events per time unit, per time period, and we're doing this by annually, so it's per year. I think I need to say events per person per time period. And now the reciprocal of a rate is the average interval between events. So let's see. Let me say it this way. If B is very close to D, then B over D must be very close to 1. And now I'm going to make a claim, and my claim is that if the death rate D is close to 3% per year, then, by the way, we refer to this as not 3%. In demography, we often give our crude birth rates and our crude death rates. We express them as per 1,000 people. So 3 per 100, 3% is 3 per 100. We actually usually refer to this as 30 per 1,000. And so it's so universal that we refer to these rates as per thousands that sometimes we just drop the per thousand. We just say the birth rate is 30, or the death rate is 30, or the death rate is 10 or 9. And demographers are so used to this that they will automatically in their heads add per thousand. In any event, if we have a death rate of 3% per year, then I want to say that 1 over D is going to be 1 over 0.03, and that thing is going to be close to 33.3. 1 over 0.03 is going to be 33.3, and that thing is going to be close to the average length of life. If the death rate is around 3%, then on average, the average length of life has to be 1 over 0.03 or 33.3 years. And we call this thing not only the average length of life, we also call this thing the life expectation or life expectancy at birth. And we give this a special symbol. We call this E0 for the expectation of life at age 0. And it turns out that we do think that over much of human history, the life expectancy or the expectation of life at birth is somewhere in the range of 30 or 33 or so. So, if 1 over D equals expectation of life at birth E0, and we saw earlier that B over D for most of human history was going to be close to 1, then for much of human history, let's see, 1 over D equals E0 and B over D is close to 1, then for much of human history, when the growth rate R was very close to 0, then B times E0 was very close to 1. The birth rate times the expectation of life at birth was very close to 1. And this is something that's so important that I'm going to draw a box around and rewrite it one more time. And I'm going to give this a name. So if the R equals 0, not close to 0, but actually is 0, and has been for a long time, then we call that kind of population a stationary population. If the growth rate actually is 0, that means that the size of the population does not change. It is constant. It doesn't change. We call that a stationary population. And in a stationary population, B times E0 equals 1. And this is so important. We call this thing the stationary population identity. And I'm going to draw a box around this, and I'm going to underline that. This is the stationary population identity. Now it turns out that, as we said, that's only true if the growth rate R is exactly equal to 0. If R is not 0, it's close to 0, then B times E0 is close to 1. It's not equal to 1. It's only equal to 1 when the population is stationary. Let me make a example. And it turns out that in the United States, I looked this up, about 5 years ago, in the year 2015, that was, I guess, 6 years ago, E0 for both sexes combined in the United States at the time was 79.8. R was not equal to 0, but R was small. I'm going to claim that 79.8 is close to 80. And I'm going to say 1 over 80, so this is E0, 1 over 80 should be close to D. That turns out to be 1.25% or 12.5 per thousand. And if R was close to 0, then B times E0 should be 1. So that must mean that B should be close to 12.5 per thousand. And if you look it up, it turns out that in 2015, in the US, the birth rate B was 12.4 per thousand. So that example puts us in the right ballpark. I think we're going to stop now.